to reaction rates notes. We're going to start off by looking at the reaction mechanism. So the reaction mechanism is something we haven't talked yet about in chem, but it's really looking at what is exactly going on. So for example, I have this one equation here that in order to get this reaction, the net, this is actually occurring. So chlorine is matching ozone, that's O3 in the air, to make this chlorine-oxygen compound and oxygen. The elemental oxygen goes off, floats into our atmosphere. However, a single oxygen, and this is an atom, not an ion, reacts with this chlorine-oxygen from before to make chlorine and O2. So in the end, oxygen plus the O3 makes 2O2. This seems very familiar from when we were doing Hess's law and getting these net reactions. Now, the intermediates aren't shown up because they're first made and then they're used up, as indicated by the ClO. So what's made is used up, and we've talked about it like this with Hess's law, but in Hess's law we're using those original reactions to get a secondary feature. So down here I have another example that in this case, to get our net down at the bottom here, I2 plus H2 equals 2 hydrogen iodide, you would actually need in practice the iodine molecule to break into 2 iodine atoms. If that doesn't occur, you cannot make hydrogen iodide. So in practice, iodine atoms collide with one hydrogen molecule to make 2 hydrogen iodine molecules. This creates a big difference when we talk about reaction rates, because if you prevent iodine from breaking down into atoms instead of a molecule, you'll never get hydrogen iodide. Now with all reactions, they happen because of enough collisions. Molecules are always moving around, vibrating, colliding. However, there's two things needed enough in order for reactions to occur. One is enough energy, which we've talked about before, and two is correct orientation. So I'll zoom in on this picture here. So the idea is that if you want to have AB, which I believe we have A being the small one, right? A is small, B is large, that if you want these to overlap, you need to have these ball models overlap, in which when the ball models overlap, those are overlapping orbitals sharing electrons, creating a bond. So in this case, this first one, everything lines up, the electrons are there, but it's too gentle. There's not enough energy pushing them together in order for them to react. In the middle portion, there's no way that both A atoms can overlap in order to bond and therefore make a A2 molecule. In the what's called an effective collision, it needs correct orientation and energy. So an effective collision is a successful collision and therefore can have a chemical reaction occur. So if you want to increase a chemical reaction speed, you need to increase the effective collisions, or vice versa. You want to slow down a reaction, you need to enable it to where there's not an effective collisions going on too often, so therefore it will slow down or not react at all. Now, we've talked about bonds being broken and bonds forming, and we've always said that when you have reactants and you need to break bonds, you need to add energy to this. We never gave it a title, but what it is called activation energy. This is why things might be together but don't react immediately. Once it starts releasing that energy, then it maintains this in order to complete the reaction. So at some point, if we look at this little energy diagram down below, our reactants have some amount of energy called enthalpy. You need to add energy in order to break those bonds, and up at the top, something special is formed. That is when bonds are breaking and bonds are forming. In that energy, though, of bonds forming, energy is always going to be decreasing, coming down to where you have the products from the top of this hill. The overall change is the heat of the reaction, And if we wanted to reverse the reaction, we need to put in more energy than what we did for the other one in this case. So the thing that is made is called the activated complex. This is where bonds are being broken and new bonds are forming. This doesn't really exist. We don't know their structures. These are just an example model to give the idea that at one point you have all of the atoms in one location making a successful collision, and when they make a successful collision, then we have a new product instead of the reactants that we had before. So there are several factors that affect reaction rates. Nature of reactants, surface area being larger or smaller, temperature being higher or lower, concentration being higher or lower, and then the presence of a catalyst. Remember, a reaction or successful collision occurs because of energy and orientation. So if you can increase one or both of these, you're going to have an increased rate of reaction. So we'll start off with the reactants themselves. Some are more reactive than others. Now, what things make them more reactive is, we go back to the first semester, maybe things like ionization energy. To where if you have a lower ionization energy and there's 500 kilojoules present, then that's going to make it to where more atoms are able to react with that existing energy. Some things might be larger or smaller, to where they have an orientation that's either easier or harder to line up with. And so if it was easier, maybe because it's very large and it has a lot of places it can react on the compound itself, then it's more likely to be reactive. However, if you have something that's very large, like a large alcohol compound, which has an OH at the end, if the OH is the only place it reacts, there's a lot of place in that molecule where it's not going to react. So just itself, it's going to be a lower reactive molecule than something like methanol, which is one of these, and it's very easy to get to that OH reactive group. So again, the reactants can be different based upon just their geometry and their orientation. It also might be affected by number of collisions given per time. A bigger molecule is harder to move around compared to a smaller molecule, so that would also have an influence. If we think of surface area, like dissolving, it allows more contact of the reactants, and if it can happen all at once, then it will occur faster. That's why I'll direct you to this picture here. So in this case, the red dots are wanting to react with the green dots. However, there's only so many dots that can interact in any given time around there. If I wanted to count it, I'd say there's 4, 8, another 9. There's so many, let's say that. However, when we look at these smaller pieces, when smaller pieces have a higher surface area, any of these on the outside will have a possibility of reacting, which, based off of just drawing around the perimeter of these shapes, you can see is far more of the same blocks that we had before. Even though we didn't change how many red dots there were, how many of one of the reactants there were. So the idea here is that if they need to collide, meaning interact, we have many more possibilities with smaller pieces. And remember, small pieces is higher surface area. And of course, the opposite is true. So you think of how this would change the amount of energy or orientation or number of collisions per given time. So next is talking about temperature. We know that temperature is related to kinetic energy. So if that's related to kinetic energy, the higher the temperature, the higher the kinetic energy. Likewise, the lower the kinetic energy, the lower the temperature. So keep that in mind as we talk about higher or lower. Now, with this concept here, this has twofold. Because of the fact that we have more kinetic energy in something that's hotter, let's undo that, more kinetic energy when hotter, then you're going to have more collisions at a more successful energy. On the other hand, you also have, remember, kinetic energy is 1/2 the mass, which doesn't change based upon temperature, mv squared. So something that has a higher kinetic energy also moves faster. So what that means is that you have at higher energy, you have more frequent and successful collisions. So successful because of the kinetic energy component, more frequent means more per second. So you are going to increase that a lot. That's why things, when they're hotter and reacting, can really get out of control very quickly, because of the fact that higher temperatures will make this happen almost under 2 factors instead of just 1. Our next stop is concentration. Concentration means the amount. So we've often talked about molarity, and when we've talked about substances, you've seen it on your bottles before, and that's an amount of moles dissolved in 1 liter. So if we have a higher molarity, there's more moles dissolved in 1 liter, meaning there's more of the substance in 1 volume, in this case a liter. So the way this works is that if you have different things here, A and B, if you only have one of each, they can only collide in 1 possible way. If you have twice the concentration, now we've gone up 4-fold. So you can see that there's this squared factor. Likewise, even if you just added 1 more A, you can see that you're not just adding 1 more collision. And likewise, when we go from here, you go from 4 to 16 when you double the concentration again. This also has a possibility of having very reactive possibilities. As you double the concentration, you're squaring the possibilities of things reacting. And quite often, a lot of these things are exothermic. So if you're squaring the factor of how often they can collide, and they do, then they're releasing heat, which increases the speed of the reaction, more successful collisions. And this is where chemical reactions become explosive or really get overwhelming for the person doing them. Our last one is a catalyst. A catalyst is some kind of substance. In biology, we call them enzymes. They can be simple things like platinum is a catalyst, rhodium can be a catalyst, or they can be very complex molecules. But essentially what they do is they provide an energetic shortcut to the reaction. So if we're talking about going from a reactant to a product, under normal circumstances you need to have 75 kilojoules of activation energy in order to go and break those bonds. If you were to have an iodine molecule in there, iodine ion, it takes less energy. The iodine provides some kind of intermediate at a lower energy state in order to be reacted with. Then you could even have an enzyme, which we can see has a dramatic effect, going from 75 to 4, or you could have some weird heterogeneous process that kind of goes up and down, has many different steps, but you could see has very little energy needed in order to have it react. So all of this plays a role, and it can play a role in a couple different ways. The energy can be helpful by forming something new. Other times, like when we do electrolysis, that's the electrical separation of hydrogen and oxygen in water, a platinum electrode, which you might remember platinum being positively charged, will attract all of the water molecules with their negatively charged oxygens and part of the positively charged hydrogens to really orient themselves in a way that you have oxygens all lined up and hydrogens lined up. And this orientation helps a lot because in order for you to get hydrogen, H2, and O2, oxygen, they need to be close together. And because you're running electricity through it, you have enough energy, you have orientation, you get a successful collision, or what's also known as an effective collision. Be sure to answer the rest of the questions and see if you have any questions when you come in. Talk to you later.